Hi everyone, how are you all? Okay, so let's get started. Hello Mahesh. Okay, so today we are going to start continuous random variable. So let me just start. Okay, so we have seen expectation of discrete random variable and more about discrete random variables already. But now we are moving towards continuous random variable, right? So let's just see. So I think a bit of that we have already covered in the module one. So here we have covered the about the continuous random variable. Have you seen this particular lecture? How many of you have seen this lecture? Okay. So in the module one, have you seen this lecture? Most probably you have seen, right? Okay. So in the discrete case, we used to have PMF, which is probability mass function. In the continuous case, we have PDF, which is probability density function. Okay. So what is a continuous random variable? A random variable which can take any value, right? Any real number. So we will see more. Don't worry. Let me quickly go over this particular slide. Okay, in just 5 minutes, and then we will see this continuous random variable again. Okay, we will review all these things. So we have seen that if you want to find out the probability, then you need to integrate this PDF, right? So this is a PDF. This is not a probability. So for example, this used to be the probability in case of PMF, but this is not probability. Okay, this is probability density function. So what does this mean intuitively? It means if you have, let's suppose this curve, then what does this mean? It means that you will be finding the probability after the integration, and if the bar is higher here, then what does this mean? It means the probability here in this region is higher. So basically, the probability that the x is taking the value from 3 to 6 is actually higher, right? Okay. So don't worry, we will see again. Okay, all of these things we will see, we will review again actually. So this was the one of the lecture that we have already covered, right? Okay. Now let's just start with today's lecture directly. Okay, so let's see this case. Let's suppose this is one bird. This is, I think, another bird. So this is saying that I'm 3 feet 1 inch tall, and my weight is, for example, 34.16 gram. Okay, so this bird is telling exact details, which means the discrete values. That these are the details of my you can say that details of my body. Okay, that I'm 3 foot 1 inch tall, and my weight is 34.16 grams, right? So these are the discrete value. But if you have, sorry, these are the continuous values. For example, that this particular height could not be exactly 3 foot 1 inch. It could be 3 foot, maybe 1 inch. Instead of 1 inch, it could be 1 0 0 0 0 0 0, something like this, right? One. Okay, it could be something like this, right? So what I'm trying to say here is that for example, if the weight is 334.16, then it could be the approximate weight, which means there is no guarantee that weight is not this much. Okay, not this much. So which means that the weight can take any of the continuous random value. But here, if you have the discrete value, for example, 8 lakhs, 4 spots, then these can be measured by discrete random variable. And these can be measured by continuous random variable. So what do I mean by that? Let me just explain it more from Stanford. Okay, let's just see. So what they're saying, that to make a transition from thinking about discrete random variable to continuous random variable, let's just think about some experiment. Okay, imagine you're running to catch a bus. You know that you will arrive at 2:15 p.m., but you don't know exactly that when will bus arrive. Okay, so you want to think the arrival time in the minutes past 2 p.m. as a random variable t. So which means that you don't know exactly that when will bus arrive. Maybe you can think that okay, it will arrive at maybe 5 minutes of interval after two. Okay, or maybe in this after two, maybe it may arrive after two. Maybe it may arrive between 2:15 to 2:20. So what I'm saying, that bus may arrive. Okay, you want to maybe guess. Okay, not exactly that bus will arrive at 2:16. You are not very much interested in that what bus will arrive at 2:16, 2 minutes 16 seconds. You are generally interested that bus will arrive at between 2:15 to 2:20 or not, or maybe bus will arrive between 2 to 2:05 or not, right? Something like that. So you are more interested in the range instead of having more interest in the discrete value that, okay, you are interested in 216 like that. So to, illustrate it more, what I'm trying to say here is that, uh, so we immediately face a problem from discrete distribution. We would describe the probability that a random variable takes on a exact values. This doesn't make sense for the continuous value. For example, it doesn't make sense that what is the probability that bus will arrive exactly at 216. Why it doesn't make sense? Can anyone tell me? Why it doesn't make sense to say that bus will arrive exactly at 216? Because see, there is no, the fixed measurement that you are interested in 216 and you are not interested in, for example, you are interested in 216 exact 216, you are not interested in 216 0000001. Who is going to measure that whether it has been followed and it has not been followed? So you are not interested that bus will arrive exactly at 216 and no microsecond, no millisecond here and there. Are you really very, very interested to know that, okay, bus is not getting late or not arriving early, even a microsecond or even a nanosecond? No, right? So basically the measurement here, you can't actually measure till too much precision. So that is why we are not very interested that bus will arrive exactly at 216. For example, uh, for example, what is the probability that bus will arrive exactly at 2:17 p.m. and 12 point this some random number seconds? So basically 2:17 p.m. and along with that, let's suppose at daytime it is 2:17 and exactly at this second also. So generally you're not interested, right? So that is why they are saying that it doesn't make sense to say that bus will arrive exactly at this and not even a nanosecond here and there. Similarly, if I were to ask you what is the probability of a child being born weight exactly equal to this, okay, so what is the probability that the child is going to have this much weight, exactly this much weight? You might recognize that question is ridiculous. No child will have precisely that weight. Real values can have infinite precision, and as such it is bit mind boggling to think about the probability that a random variable takes on a specific value. So basically this particular line is very important, that real values can have infinite precision. Okay, that is the point. Because they can have infinite precision, it doesn't make sense to ask for the exact value, okay, for the real numbers. So since real values can have infinite precision, so it doesn't make sense, right? It doesn't make sense to ask for exact value with real numbers, right? Is this okay to everyone that we are not interested in probability of the exact value? Okay, that what is the probability that x is taking this exact value? Is this fine? Okay, great. Now let's go to the more examples that what I'm trying to say. So by the way, these motivation I've taken from Stanford University. So what they're saying, instead let's try discretizing the time. So our continuous random variable by breaking it into 5 minutes chunk. Okay, so you can now think something like this: the probability that bus will arrive. Okay, this might be PM. Okay, bus will arrive between 2 p.m. and 2:05 p.m. as an event of some probability. So basically, instead of exactly at 2 p.m., you are more interested, for example, between this 5 minute interval. That what is the probability that bus will arrive in this 5 minute interval? Okay. Okay. So this is something that we are going to study in today's lecture. That how to use this continuous random variable, how to find the probability that bus will arrive between this 5 minute interval and so on, right? Okay. So we have focused on discrete random variables so far. We now move from discrete random variable to continuous one. To review, a continuous random variable is one which can take any value in an interval. For example, how long will you have to wait for the next bus to arrive? Okay, so these things you might already be knowing that the continuous random variable does not have, the point probability, which means if you want to find out the point probability, then it is zero. Okay. Anyway, we will see this again. So let's just start this continuous random variable. Okay. So in the continuous random variable, we do not have PMF, which is probability mass function. Why? Because it is impossible to list out all the possible values in an interval. So a continuous random variable cannot be displayed in the tabular form in the sense that, okay, what is the probability of X being 1 or something like that, right? It is not possible for the continuous random variable. That means that a continuous random variable does not have a PMF. The probability function of the continuous random variable is called PDF, which is probability density function. Okay. So let's just see what is this. So PMF, you already know that probability of some particular, let's suppose X equal to 1, this is, let's suppose X equal to 1, this much, X equal to 2 is, let's suppose, or X equal to 3 is having this much probability, X equal to 4 is having this much probability. So this is PMF. What is PDF? PDF is something which is continuous probability, right? It doesn't have exact discrete value. For example, it is just like, you can understand something like that these are the weights, okay? For example, 3 kg weight, okay, this is, let's suppose, 5 kg weight, this is, let's suppose, 2 kg weight, or 0.2 kg weight, or something like that, right? These are the weights, but this is not just one weight, which means the probability is not, clustered only on one point. It is just like you can understand like a stick, okay? It is just like a stick where weight is not at just at one point. It is basically distributed all over the place. Okay, probability density is there all over the place. It is not a probability mass which is just clustered on only one point, right? So what does this mean? Let's just see. So suppose that there is a function f fx, right? Fx. This function could be anything. We will see that what are the forms of this function. But this function, let's suppose, is there. This function is called PDF. If you can find the probability between A to B, just using this formula, right? We have seen these things. So for example here, okay, in the module 1, we have defined that probability density function. What is that? A random variable X has probability density function fx if this probability of being between A to B is can be defined like this, right? So that's why probability of A equal to probability of any point, which means whenever A is B, A and B are same, it is zero. Integration from A to A is zero. So for a valid, and also for a valid PMF, for a valid PDF, minus infinity to infinity, if you integrate it over all the possible values of X, then you will be getting 1. Okay, minus infinity to infinity. Okay. Also here, this PDF can take any value, which means, for example, this fx can take even the value 10. Okay. So this is not a probability again. Since it is not a probability, it can take any value. But whenever you integrate, whenever you find actual probability, it will be obviously less than equal to 1. Okay. So here, it is possible that fx can be greater than 1. Okay. It is it is the area under the curve, any part of fx which can't exceed 1, which means this area under the curve. Okay. This is the probability. But fx is not probability. So PDF is not probability. If PDF is not probability, then can anyone tell me that what does this signify? It basically tell you that it is not the probability, but let's suppose I give you something like this. Fx is something like this, right? Then you can tell me by looking at this graph that, okay, this region is having higher probability. That, let's suppose, this is the arrival time. This is the PDF of the for the arrival time of the bus. Then you will say that, okay, between 3 to 6, there is a very high chance that bus will come, right? But there is a very high chance between 3 to 6. Okay. The probability that X can take any specific value is actually 0. Okay, now let's just try solving few questions, and after that you will be understanding PDF more, and then we will be, doing some more practice with the continuous random variable. So let's just see this example. So what this example is saying, I want to describe a PDF to, so they want to have some PDF, okay, some probability density function to describe the amount of time I wait for the bus in the morning, assuming that I don't look at the schedule and leave at the house at the random time. So they are saying you leave the house at the random time. Bus arrive in every 10 minutes. Okay, what is the PDF of describe? Okay, so how long I have to wait? Okay, you are basically saying that you arrive at random time. Okay, you arrive at bus stop. So arrive at bus stop at random time. You arrive at bus stop at random time, right? Suppose. Now, what is the PDF of your arrival time? Okay, what is the PDF of the arrival time of bus? If bus can come, anytime, okay, and bus arrive actually in every 10 minutes, and then we will find out the probability that what is the probability that I have to wait more than 8 minutes. With this assumption, my possible waiting time is 0 to 10, and all of these are equally likely, right? So I can wait okay, they are asking PDF of the waiting time, basically. Okay, PDF of the waiting time. I mean, both are actually same, but anyway. Okay. So what could be the possible waiting time between 0 to 10, right? This is the possible waiting time, that you might have to wait 0 seconds, or you might have to wait at most how many seconds? Oh, sorry, minutes. 10 minutes, right? Why? Maybe the moment you reach, bus has just left. Okay, and the next bus may come after 10 minutes, because bus is coming in every 10 minutes. So minimum 0 and maximum 10. Okay, this is your waiting time. I mean, this is the value that your random variable x can take. So basically, you can say that the x, okay, so x can take any value between 0 to 10. What is x? Your waiting time, right? Your waiting time. You may wait 0 seconds, 0 minutes, or you may wait 10 minutes. Now tell me, if I just ask you that what is the probability that you may be waiting, let's suppose, uh 1 minute, which means between 0 to 1. This is basically same as the probability that you are waiting between 1 to 2, right? Because bus may come anytime. So in the first, what is the probability that your waiting time is first 1 minute, or maybe what is the probability that bus is coming in the next 1 minute? So basically, these two probabilities are same, right? So that's why you can say that, see here, that the only way to represent is that all of these are equally likely, which means all of the intervals are equally likely. So bus can come anytime. So that's why the PDF is going to be constant. Okay, which means this is also called as uniform case. I think we have already talked about little bit about the uniform. So here in the lecture one, sorry, in the module one. So but here I'm just revisiting. So let's suppose that fx is k. Then how to find out the value of k? You can just integrate it, and it should be 1, right? So here k is coming out to be 1 by 10. Okay, so let's just see more example. Probably you will get to understand more. See, if you want to find out the probability for any interval, let's suppose a to b, then you will be just integrating your PDF from a to b. So which means this is integration of fx from a to b. Okay. Okay. Now let's just see this. The length of my lectures is given by continuous probability distribution of the form kx square, where x lies from 0 to 75 minutes. Okay. So what they are saying, what is k? So can you find out the value of k? If this is the valid PDF, then what is the value of k? You need to integrate kx square from 0 to 75, and it should be 1. Okay. So from here, it will be x cube by 3 k into x cube by 3, 0 to 75, and then it will be 1. So from here, I think you can find out the value, which is k is coming out to be this, right? Okay. Now they are saying that what is the probability that my lecture is done in less than 60 minutes? Then this is the probability, right? 0 to 60. So what does this mean? It means that the random variable x, which is telling you the duration of the lecture, right? Okay. Which can go from 0 to 75. And the probability density function by which this this might vary is given like this kx square. So they are saying that to first find out the value of k and then find out the probability that it will be from 0 to 60, which means it might end from within initial 60 minutes. Okay, so let's see more examples. So I think this is okay. The probability must be probability, the total probability or the total under area under the PDF must be 1, right? From minus infinity to plus infinity. Okay. See, if x is continuous, then px of x, the point probability is at 0, right? If this is continuous, then the point probability is 0. Okay. You apply since the point probability is at 0, you apply the equal to or you don't apply the equal to, these things doesn't matter, right? We have already seen this. So what percentage of men are 6 feet tall exactly? This is actually 0. Okay. So those that are 6.0001 or 5.0 doesn't tall doesn't count. So basically the point probabilities are actually 0 in the case of continuous. Okay. So now let's just find out the value of C here. Let's suppose that your random variable X is having this particular PDF, right? Which means that you can say that the random variable takes, okay, this is 0, the value from 0 to 1. So what is the probability that it is going to take the value from 0 to 1? You can find the area under the curve, right? So which means it is the, I think, 1 by 2 into the triangular area, right? So this is base 1 into C. So it is C by 2, and then this is C. So C and this is C by 2, right? So this is the total area. So C plus C by 2 should be 1. So from here, I think you can find out C, which is 2 by 3, right? The total area should be 1. So which means what is the probability that the random variable is going to take from 0 to 1? The probability is C by 2, but it is going to take from 1 to 2. The value it is going to take from 1 to 2 is actually C. Okay. Now, if they ask you, let's suppose the C is coming out to be 2 by 3. Okay. This is 2 by 3. Now, suppose they ask you that what is the probability that X is less than or equal to 1.5? Can you calculate it quickly? So it is 2 by 3, the first area, plus this much area, right? Which is C into zero point 0.5, which is C by 2. Okay, sorry, this is C by 2 only, which is 2 by 6. Okay, so 2 by 6 plus 2 by 6, which means C by 2 plus C by 2 actually, right? So it should be C by 2 plus C by 2, which is C, which is just 2 by 3, right? Okay, this was little bit about the PDF. Now let's just see CDF also, and then we will be mixing both of the concept PDF, CDF, okay, in our questions. So let's just see CDF. What is a cumulative distributive function? Have you heard about this particular name? How many of you have heard about this particular name? Okay, just the name. I think we have talked about it in the module 1 also. Do you remember? Um, lecture, I don't remember exactly. I think maybe before that, but we have already talked about it, right? Okay. Anyway, we are again going to talk about it. So basically, CDF is defined like this. Let's suppose you want to find out f of x. Okay, this is the function of x only. It will be probability of x less than equal to x. So if you want to calculate this probability using the PDF, you can calculate, right? Which is like this: minus infinity to x. Okay. See, I'm using x here. Maybe you can use c. If you want to use c, it will be c, right? So just to not get confused, we are using by and dy. But if you are using c, you can use x and dx. Okay. I mean, what I'm trying to say here is that since we have already used the variable x here, okay, that's why they have written by and dy. Otherwise, you can write x and dx. That's also fine. Okay. So as you can see that CDF is basically the probability that x is less than equal to some value. For example, f of a. Then the probability that x is less than equal to a, right? From minus infinity, right? I mean, from the starting. So this is the f of a. Now this whole thing, this whole area is f of a. Is a value or is a function? What do you think? This whole area, it will be a function, random variable, value, what it will be? Yes, this whole thing is just a value, right? Just one value. So here, this is just one value, and this a at f of a is this much. Okay. Now, similarly, if I want to find out, let's suppose this is a. Okay, let's suppose this is a. Earlier, I think earlier maybe earlier, let's suppose this was a. Let's suppose this is b or some other value. I want to find out f of b. Then it means that from minus infinity, okay, from starting, you need to integrate all over the place. This is f of b. Let's suppose earlier it was f of a. Let's suppose it was a. Tell me f of a is greater or f of b is greater. Which one is greater? Obviously f of b, right? This is greater. Why? Because you can say that in this f of b, you have the more area, right? This is the more area that you are covering, isn't it? So can you say that the moment, let's suppose you calculate f of c, then tell me in between f of a and f of b and f of c, which one is the highest? F of c is the highest, right? F of c is the highest. So can you say the moment you keep on going on the right side, which means you keep on increasing the x, your f will keep on increasing because the area that you are covering is actually more, right? F is the area from starting to that point. So if you're starting from here, I mean, let's suppose from any value, then it is basically the moment you cover more x, the moment you have more x, your f will keep on increasing, isn't it? Okay. Is this understood? What I'm trying to say? That this relation is there in the case of CDF. That the moment you keep on increasing x, your f is keep on increasing, right? Okay. So let's suppose that here, this is the final value of x. Let's suppose this is d. So what is the probability that x is less than or equal to d? The whole area, right? Which should be one. Which should be one. Is this fine to everyone? Let's suppose this is the whole area, and the whole area is actually one. What does this mean? This is actually f of d, right? This is f of d. So what I'm trying to say here is that after uh, at A it is something, at B it is increasing, at C it is increasing, at D it becomes 1. Okay, the highest value can be 1. Now suppose if I want to find out f of E, then what it will be? Capital F of E. It will be probability of x less than or equal to E, which is same as just 1, right? Because here you don't have any value between D and E. Are you getting my point? So basically, at A there is some value, at B it is increased, at C it is increased, at D it is 1. Once it is 1, after that, if you increase the value of x, your f will remain constant, okay, which is just 1. Understood? So so it is an increasing function. Definitely it is an increasing function, okay, but the moment you hit 1, it is a constant. Okay, so you can say it is a non-decreasing function. I mean, it need not to increase at every point, because once it hits 1, it will be constant. So it is a non-decreasing function. Basically, it increases, and once it is 1, then it is always 1. This is CDF, right? Why it is increasing? Because the moment you keep on keep on increasing x, you are covering more area, right? You are covering more area. That is why it is keep on increasing. And once you cover all the area, once you have 1, then it is constant. Okay. So see here that this whole area is just one value here. Okay. Tell me, is this a valid CDF? Is this a valid CDF? How to check it? Just check whether it is increasing or not. Okay. So suppose that it is always increasing here, right? I mean, this curve may be like this, but let's suppose this is increasing. So it will be the valid CDF, right? If it is increasing, then it is a valid CDF. You just need to check whether it is keep on increasing or not. Understood? So we will solve questions, graphical questions also. Okay, that whether it is a valid CDF or not. But currently, I'm telling you that how to check whether it is a valid CDF. Now, suppose you want to find out, the probability that x is between A to B. This much, right? So what you can do, let's suppose you want to find out this probability, right? So what you can do, you have the CDF, right? If you have the PDF, then what is the formula? Integration of A to B fx dx, right? Using PDF. But using CDF, can you do it? If you have the CDF, then what you can do, you can find out the whole area from starting. CDF is always from starting, remember, okay? CDF is always from starting. So from starting, you can find out this whole area. From starting, you can find out till A. And then you can subtract, isn't it? So it will be capital F of B minus capital F of A. So I can say that if you want to find out the probability that x is between A to B, then obviously using PDF, you can do it like this, right? And using CDF also you can do. How? Maybe you can understand like this, that from starting, right? From starting, using PDF itself, you will be doing from starting, right? From starting to B, and then from starting to A, right? Okay. Which is nothing but CDF, which means F of B minus F of A. So using CDF, you can do like this. Understood? Okay. So let's solve questions, and then you will get to understand more. Okay. So these are the properties of the CDF, which means it is non-decreasing. The highest value can be 1. Okay. Whenever you're approaching, you keep on increasing, and if x is infinity, then it is the highest value. Before that also it could be the highest value, but the highest value is actually 1. And x of minus infinity, which means the lowest value will be 0. Okay. So this is the highest value 1, lowest value 0. Okay. Now tell me, if I draw a CDF here, tell me, let's suppose this is a CDF, right? For x equal to 0, there is some value like this, okay? For x equal to 1, this is the x. This is constant. Is this valid CDF? Is this valid CDF? What do you think? See, it seems valid. Let's just check. It is non-decreasing, yes. Okay, at the highest is 1. Okay, let's suppose the highest is at some point. After some point, let's suppose it is the highest value that it is getting as 1. Okay, maybe at x equal to 5, and then it remains 1. But interestingly, the minimum value is not 0 here. Okay, for x equal to 0, or maybe let's suppose it is starting from here, the minimum value is something, right? Is this possible? No, right? So here here I'm saying that minimum value is not 0. That's why not valid, right? Minimum value is not 0. Hence, invalid PDF. Understood? Sorry, invalid CDF. Now, let's suppose I ask you this. Let's suppose I ask you this. Is this valid? Sorry. Is this valid? Yes, this is valid, right? This is valid CDF. Okay. Okay. So don't worry, we will see the examples and after that it will be more clear. Tell me this true or false. Probability that you want to find out x is greater than or equal to a using the CDF they want to find out. Okay, not using the PDF. Using the CDF they want to find out. Is this true or false? This is easy question. It is true, right? Why it is true? Because this probability of x greater than or equal to a is nothing but 1 minus probability of x less than or equal to a. Right? This equal or doesn't equal doesn't matter in the case of continuous. So which is nothing but 1 minus f of a. Right? This quantity is f of a, so hence it is true. Okay. Now let's just solve this question. Let's just see what they're trying to say. So what they're saying is that in the last class, okay, maybe let's not worry about it. We said the PDF of this. So let's suppose this is the PDF. Then they're saying what is the probability that I have to wait more than 5 minutes, which means they're asking what is the probability that x is greater than or equal to 5. So how to solve it? This will be 1 minus f of, or maybe 1 minus probability of x less than or equal to 5, which means 1 minus f of 5. F of 5 is nothing but integration from start to 5 and your PDF, which is 1 by 10 dx, right? So you can solve this. What is the answer that we are getting here? F of 5 is actually 1 by 2. Okay. So this is going to be, yeah, this is going to be x. So it will be, so let me just solve it. 1 minus x by 10, 0 to 5. So it is 1 by 2, right? So it is 1 by 2. So answer is 1 by 2. Okay. Now suppose they ask you to find out the CDF also. Okay, CDF as a formula. So how to find out the CDF? Let's just find out the CDF. So what is the CDF here? I mean the complete CDF. So basically, this is f of x which we want to find out. Okay. Then you can say if x is less than or equal to 0, right? For x is less than or equal to 0, maybe you can divide it into 3 parts. Maybe if x is less than or equal to 0, then there is no density, right? If there is no density, then the CDF will be 0. Okay, initially CDF is 0, so it is 0. Okay, so the moment x is from 0 to 10, it will be increasing. Okay, because there is some density, and then I think after 10, CDF will be constant, right? So how much it will be? 1. So initially it is 0, at the end it is 1. Okay, which means if x is greater than or equal to 10, then it is 1. The only thing is that we want to find out between 0 to 10, right? Between 0 to 10. If x is between 0 to 10, then f of x is nothing but you can always integrate fx, which is 1 upon 10, 1 upon 10 dx, which is x by 10, right? So here it will be x by 10. So the CDF is generally a piecewise function. Piecewise means that that from starting, let's suppose it is taking some value, then in between it is taking some different function, and after that it is always constant, right? After some point in time. So generally the CDF will be like this between the interval. Okay. So wherever the density is, it will be there. Before the density, it will be 0. After the density, it will be 1. Wherever the probability, the valid probability density is valid in the sense like non-zero. Okay. So wherever the non-zero probability density is that, then at that point in time, your CDF will be defined. So this is seeming like the straight line. So you can say it will be something like this, right? So this is the sketch of CDF. So what I'm saying here is that, what is the sketch of PDF? What is the sketch of PDF? The PDF sketch is just constant, which means this seems to be the sketch of PDF, you can say. It is just like a uniform distribution. From 0 to 10, it will be just like a constant, which is 1 by 10, right? This value is 1 by 10. This is sketch of PDF. So now you see that this is some area, right? From 0 to 1, there is some area. And then if you go to 1 to 2, then this area will be increasing. At 10, it will be 1. The area is 1, right? At 10, the area is 1. And after that, you don't have the PDF here. So that's why it is always 1. So this is the sketch of PDF. This is a sketch of CDF. Okay. I hope both sketches are clear. So this is just a constant. So this is a sketch of PDF. And then CDF is generally you can say increasing in this range, right? So basically it will be increasing. Here it is increasing with the constant rate, which means with the linear or with the straight line. Okay. So we will see more example of this sketch and all, and it will be more clear. So for example here, if your PDF itself is a straight line, okay. So what is the integration of x? What is the integration of x? It is x square, right? So if the PDF itself is a straight line, then the CDF will be something like x square, right? Something like x square. Okay. So this is CDF. And after some point in time, it will be constant. It will always be constant after some point in time, which is 1, right? Maximum value could be 1. Understood? Suppose the PDF is constant. Let's suppose it is C or maybe 1 by 10 or something. Then what is the integration of C? It is CX, right? It is a straight line. So it is a line. Okay. In this range. In this range. Before this 0, after this 1. Understood? Let me know if this is clear. Suppose your PDF is like this. Okay, maybe some function. Then the CDF is looking like this. Okay. So here is the CDF decreasing? Tell me. PDF is decreasing after some point in time. Is CDF decreasing? No, right? CDF cannot decrease actually. See, see, here you are increasing CDF. I mean, till this point also, you are basically increasing the area, you are increasing. But here now you are increasing only, but the increase rate could be, you are now adding little. Okay, this is little portion, and this is more or little portion. This is little portion. So basically now now also you are increasing the area, but you are adding. Okay, your increment is little slower, right? So rate of increment could have decreased, but CDF is not decreasing. Anyway, these things are not much important as at this point in time. We will see this rate of increase also, which means double derivative of x. Okay, in calculus. So here the rate of increasing has decreased, but the function itself has not decreased, which means CDF will always be increasing, but the rate of increment could have decreased. Okay. So we will see these things in calculus, but it is always increasing function. Okay. Now let's just see which of the following statements are not necessarily true about the probability density function. Is this necessarily true? Probability density function. They're not asking cumulative density function. They're not asking about the CDF. They're asking about the PDF. Do you think that PDF has to be less than or equal to 1? No, right? Okay. What about this? I think this is true. I think this is also true. From A to B, you want to find out. Okay. Uh, is this true or there is something wrong? Yeah, I think this is okay. What about this? Okay. So Bhargavi Roy is saying that this C is also not necessarily true. Why that is the case? Okay. So A is not true. A is not true because that this is the PDF. This is not probability. Okay. This is not probability. Remember, since it is not probability, it need not to be less than or equal to one. I think there are many instances where we have seen this. Okay. In the previous module also we have seen that it could be greater than one. PDF could be greater than one. See here, for example, this could be 10. Okay. So PDF could be greater than one, but the integration is not greater than one. Right. Is this greater than or equal to zero? What do you think? This is interesting. PDF, does it have to be greater than or equal to zero? Always? Answer is yes, because suppose there is a negative PDF. Okay, which means let's suppose this is a PDF, which is fx. Let's suppose this is negative. Okay, for some reason it is negative. If we want to find out this integration, then obviously the integration will be negative. And integration is probability, right? Integration is probability. So the probability cannot be negative. So that's why it has to be greater than or equal to zero only. So what I'm saying here is that this is true. The reason is that the probability of x in any region, right, is greater than or equal to zero. This means if the probability is greater than or equal to zero, then this the PDF, the integration by which the probability is getting calculated. This this value, right, cannot be less than or equal to zero. So this also has to be greater than or equal to zero. Okay. So these are the four options. I think not necessarily true. I think A is the answer. Okay. They are saying C is also the answer. Uh, from A to B, if you do it, then you will be getting the probability, right? Okay. Let's just check why C is not the answer. So generally it is true only, but if the function is this PDF, right, this fx is basically, as we know that we need to calculate this whenever we are integrating, then we need to calculate piecewise, which means that let's suppose this is a uniform PDF, right? From let's suppose some interval from A to B, and there's a constant PDF, right? Is this a valid PDF? Yes, right? So let's suppose this is some B minus A, 1 upon B minus A, right? So this is a valid PDF. This is a uniform PDF. But let's suppose this is 1, this is let's suppose 2, right? Then this will be 1 by 2. Let's suppose I say that if I want to find out the probability from 0 to let's suppose some value, let's suppose 1.5, right? Which means probability from 0 to 1.5. Okay. So I can't directly integrate. I mean, I need to integrate piecewise from 0 to 1, it is 0, and 1 to 1.5, I need to integrate. So the only reason why we are saying that it is not necessarily true, maybe because it is not even differentiable, right? It is, see, this is a sharp edge, right? Initially it is 0, and then this is sharp edge. For the sharp edge, it is not differentiable. So for the smooth edge only, it is differentiable. We will see this in the calculus, but this, since it is sharp turn, so it is not even differentiable. So it may not be even differentiable in that particular range. So generally we need to do it piecewise. That is the only reason we are saying that, okay, this is false, in the sense that it is true only. It is true only in general, in the sense that in the common sense, whenever it is defined. But you are saying that, okay, from non-zero to from zero to non-zero, if you're transitioning, okay, and if you're taking this range, then in general you will say it is false. Okay, because it may be the case that it is discontinuous itself, right? I mean, it is not even continuous. If it is not even continuous, how it can be differentiable? Okay, so that's why we are saying it's false. May not be. So not necessarily true, uh, because it may not be even continuous. Okay, for example, this is, let's suppose, 1 to 2, and you are finding out the probability from, let's suppose, 0 to 1.5. Okay, so from to find out the probability from 0 to 1.5, you can't just directly integrate something, right? So basically you need to do it from probability from 0 to 1, which is 0, and then from probability from 1.5. Maybe let me go to the next page. So basically, this is 1, this is 2, this is 1 by 2. So to find out probability from 0 to 1.5, you need to find out it separately, right? 0 to, you will say 1, and then 1 to 2, right? This is 0. You can't directly integrate just one thing, right? This is 0, and then from here you will be integrating 1 to 2. Sorry, 1 to 1.5. Okay. So maybe this is the reason that they are saying it is false. Okay. Now let's see this question. So what they're saying, which of the following statement is a correct way of computing P of x greater than 2? Is this the correct way? Tell me. Is this A correct? No, right? A is not correct. Why? This is not the probability that x is greater than 2. Okay, and in fact, this is not the probability of anything. So obviously this is false. What about this? For greater than 2, you will be doing 2 to infinity? Yes, right? You will be doing 2 to infinity. What about this? The third one? So actually it is just a notation, but we write the small x, right? We will be differentiating with respect to small x. So we don't have the capital X here. So that's why this is no. Okay. What about this? Is D correct? It is less than equal to 2, right? So this is false because this is probability of x less than equal to 2. This is true. So you can say B and E. So F is the correct answer. Okay. Okay. So so till now, what we have been doing, we have been calculating the CDF using the integration, right? If we integrate, then we can calculate the CDF. But if CDF is given, then how to calculate the PDF? So basically, now we are seeing the reverse way, which means if the CDF is given, okay, let's suppose from CDF, if we want to go to PDF. If PDF is given fx, then how to find out the CDF? CDF will be f of maybe a, it will be integration of minus infinity to a f of x dx, right? From here to here, we know this is done. But if we already have the CDF, then how to get this PDF, right? Let's just see this. So for example, let's suppose you already have this CDF. Then to get the PDF, you can simply differentiate, okay? So which means you can differentiate whatever is the value, okay? So let's just see the example. For example, the CDF is given to you. Now you want to find out the PDF. What you can do? You can just differentiate this piecewise, right? So if you differentiate each of this term, 0 differentiation is 0, 1 by 3 x square differentiation is this differentiation is this differentiation is this, right? That's very, very easy. Okay. This differentiation of piecewise function, these things, if you have difficulty, don't worry, we will be covering in the calculus. Okay. We will be covering everything in the calculus. Okay. Now, let's just see the next question. Let's suppose this is the CDF which is given to us. Now, how to find out the PDF? How to find out the PDF? You can just differentiate, right? So what you can do, you can just differentiate each of the term. Okay, that's also very easy. Let's do the next question. Suppose that they have this as PDF. Okay, and then they're asking you what is the PDF of this. This is interesting. So they have given you some PDF of, let's suppose, some random variable x. Then they're asking you what is the PDF of this 2x plus 1. So what we can do here? Can you just write instead of x, can you write x plus 1? Okay, it doesn't work. 2x plus 1, it doesn't work that way. Let's suppose this is y. Okay, so what you can do, probably you can go by a CDF. Okay, this is one of the way to calculate this PDF of another random variable. You can say what is the probability of less than equal to a. This is nothing but CDF, right? Or maybe you can write it a small y, whatever is okay with you. Okay, now let's just write it a small a. Okay, this is CDF, which means this is f of for y it is CDF. So you can say for y it is CDF f of a, right? So what it will be? It will be the probability that 2x plus 1 is less than or equal to a, right? So it will be, maybe let me go to the next page. Okay, they're writing it by. So this is, let's suppose, gy. So it will be something like this, that x is less than or equal to y minus 1 by 2. And this probability we can calculate. Why? Because for the x, we can calculate any probability, right? For the x, we can calculate any probability from 0 to y minus 1 by 2. You can calculate this probability, which is coming like this. Okay. So now you have CDF of y, right? Now you have CDF of y. CDF of y. Now, once you have the CDF of y, you can find out the PDF of y. How? You can differentiate it. That's a very clever way, isn't it? Okay. And if this is defined from 0 to 1, then this will be defined from 2x plus 1, which is 0 plus 1, to 2 into 1 plus 1, which means 3, right? So it is 2 into 0 plus 1. It is 2 into 1 plus 1. Okay. So this was actually very tricky question where PDF of one random variable is given. Now they're asking you PDF of another random variable or the function of that random variable. Now we introduced the CDF in between. We first calculated the CDF and then we found out the PDF. Okay, so we can calculate the PDF. Sometimes we need to calculate the CDF just to calculate the PDF. This is one of the example. So we have to. So basically here, what we did, we have to go via the way of CDF, which means from the PDF of X. Using this, we have found out the CDF of Y, using which we have found out the PDF of Y. Okay, this is Y. Okay, so basically, if the CDF is given, then you can just differentiate and can find out the PDF, right? Okay. So, for example, let's suppose in this case, they're asking you to find out the CDF of this X. Can you find out the CDF? I think we can just entry it and then we can find out, right? Okay. CDF is easy to find out. You can just entry it and then you can find out the CDF. So CDF is actually defined always, okay, which means irrespective of the random variable, whether it is contiguous or whether it is discrete. So CDF is always defined for PMF, I mean for discrete case also, for continuous case also. It's not like that it's always defined only for continuous or something like that. But for continuous, we only have PDF. For discrete, we have the PMF. And CDF is common for both. Let's just see the CDF for the discrete case, okay? So this is CDF for discrete case. Let's just see this. For example, if this is the PMF which is defined, then can you find and sketch the CDF? Let's just try doing it. So what is the probability that x is less than or equal to 0. This is basically f of 0, right? Which is just 1 by 4, I think. Okay. Now, what is the probability? Let's suppose x is less than or equal to 0.5. What is the probability that x is less than or equal to 0.5? Can you tell me using this PMF? Yeah, it will be again 1 by 4, right? It will be again 1 by 4. Basically, these are the masses, right? So at 0, there is some mass defined. At 1, there is some probability mass. Okay, in between, there is no probability mass. So it is 1 by 4. So you can say that it will be 1 by 4 only till 1. But the moment you have 1, then what it will be? It is including both. So 1 by 4 plus 1 by 2, right? Which is 2 by 4, which means it is 3 by 4. And now, if you want to find out f of, let's suppose, 4, then it will be probability of x less than or equal to 4, which is 1. Okay. So can you sketch it? Let's just try sketching it also. So which means only at few points it is defined. I mean, it is basically changing 0, 1, and 4, right? 0, 1, and 4. Only at these 3 points it is changing. So at 0, it is 1 by 4. Okay, it is 1 by 4. So you can say it is 1 by 4. Uh, yeah, right? So this is 1 by 4. And before 0, right? Before 0, it is basically if you say f of, let's suppose, 0 point, or maybe in some negative value. Okay, so f of -1. Before 0, it is 0, right? So before 0, it is 0. At 0, it is 1 by 4. Okay, at 0, it is a sudden jump, right? Now, it is 1 by 4 till 1. Interestingly, it is 1 by 4 till 1. At 1, there is a sudden jump. Okay, at 1, there is a sudden jump. At 1, it is 3 by 4. And it is 3 by 4 till 4. At 4, there is a sudden jump, and then this is 1, always 1. Okay, so this is 1 by 4, this is 3 by 4, this is 1. Okay, this is 1. Understood? So at these 3 points, there is a sudden jump. See, earlier, what used to happen? Earlier, you used to have some graph, maybe like this. Okay, let's suppose this is PDF. Let's suppose this is PDF. Earlier, you used to have some graph. Now, the moment you increasing it was basically the moment you keep on increasing x, the CDF was keep on increasing, right? Here also it is increasing, but it was constantly increasing, right? It was constantly increasing because there is some probability density, some probability density, so it was constantly increasing. So you can say that if you talk about the CDF, then it was constantly increasing earlier. Okay, so this CDF was constantly increasing. But now, in case of PMF, what is happening? See here, in case of PMF, this PMF is defined for discrete values, right? Which means, you can say here there is at 0 there is some value, at 1 there is some value, let's suppose at 4 there is some value, right? At 0 there is some probability mass, which is, let's suppose, 1 by 4. Okay, suppose this is 1 by 4. Suppose this is at 1 there is some probability mass, at 4 there is some probability mass, which is 1 by 4. Okay, so this is 1 by 2, this is 1 by 4. This is PMF. In this case, if you want to find out the CDF, then the CDF is not just a smooth curve. Okay, this CDF is not coming like a smooth curve. Why? Because the probability till this point, okay, you sum all these bars, okay, whatever the bars we have. Okay, if you sum this bar, this will be just 1 by 4. At 0, it is 1 by 4. Before 0, it is 0. At 0, it is suddenly 1 by 4. Now, if you sum all the bars till 0.5, it is still 1 by 4, right? So it is 1 by 4. And till 1, actually, it is 1 by 4 only. Till 1, it is just 1 by 4, right? Now, at 1, there is a sudden jump of 3 by 4. Okay, so you can say at 1, there is a sudden jump of 3 by 4. Right? And then Then if you sum all the bars here, it is just 3 by 4, 3 by 4, 3 by 4, right? If you sum all the bars. So basically it is 3 by 4 only. Till 4. Okay. Till 4 it is 3 by 4 only. The moment you have 4, then how much it is? Suddenly it is jumping. Okay. This whole means there is no value here. The value is this, right? Suddenly it is jumping to 1. This is 3 by 4. Is this fine to everyone? Let me know. Okay. So in case of continuous, the CDF looks like this. But in case of discrete, the CDF also is discrete, right? I mean, it is looking like a jump. Okay, jump. These are the jumps. Why? Because suddenly I have, okay, it is just a summation, right? It is just a summation. So suddenly I have something to sum up. So that's why sudden jumps. Can we have sudden jumps here? Can we have sudden jumps in the case of continuous? No, right? Because it's just a continuous PDF. Okay, but here suddenly you got something to add. Okay, here nothing extra, nothing extra. So that's why same, and then suddenly you got something to add, right? So that's why it is just a jumps. Can anyone tell me how much jump we are doing? How much jump we are doing? We are adding this much. Okay, what is this? This is the probability of x being 1. So we are doing at this point at x equal to 1. How much jump we are doing? Interestingly, it is just a probability of x being 1. So the jump is also defined that you are jumping with the probability of x being 1. Right? Is this phenomena clear? That here in case of continuous CDF looks very smooth, but in case of discrete, the CDF looks something like this, right? Okay. Let's just do more questions. You will be understanding more. For example, let's suppose this is 1 by 8, 1 by 8 for 0 and 3, for 1 and 2, 3 by 8, 3 by 8. Now let's just sketch this CDF. Okay, so let's just first sketch the PDF itself, sorry, PMF itself. So the 0, 1, 2, 3, right? At 0, it is 1 by 8. At 3, it is 1 by 8. Here it is 3 by 8. Here it is 3 by 8. This is PMF. Okay. Using this PMF, can you just sketch the PDF? So let's just try. Sorry, CDF. This is 1 by 8. This is 3 by 8. So see, here also let me write the 4 values. Zero, 1, 2, 3. Okay. So let's just see this. What is happening here? At 0, at 0, I mean, before 0, it is 0. At 0, there is a sudden jump, right? Of how much? Sudden jump of how much? 1 by 8. Okay. So it is suddenly jumping to 1 by 8. This is 1 by 8. It will be 1 by 8 only till 1. At 1, there is a sudden jump. So there is no 1 by 8 here. There is a sudden jump at 1, which is 1 by 8 plus 3 by 8, right? So this is 1 by 8 plus 3 by 8. Till 2 there is nothing extra, so that's why till 2 that is the same thing. At 2 there's a sudden jump, and how much jump it is? How much jump is it is? Jump of 1 by 8, right? So it is 1 by 8 plus 3 by 8 plus 1 by 8. Okay. At 3 again there is a sudden jump. How much jump? 3 by 8, which is 1 by 8 plus 3 by 8 plus 1 by 8 is already there, and then plus 3 by 8. If you calculate it, it must be 1. Okay, you can calculate it. You're getting the point? Right? So at 1, there is a sudden jump. At 2, there is a sudden jump. This jump is also defined. How much jump it is? Can you tell me in terms of the probability? There's a probability of 1, probability of 2, probability of 0. Oh, there's a probability of how much? Of which number? The probability of 1. Okay, probability of 1. So basically, the jump is also well defined here. Okay, this is how the CDF of any discrete random variable look like. Okay. CDF of discrete random variable. D means discrete. Okay. So see here, the jumps are 3 by 8, 3 by 8. I mean, based on the probability basically. Okay. See, till 0, there was nothing. And then 1 by 8 jump. Then 1 and 2, I think, have the 3 by 8 jump. And then again 1 by 8 jump, right? Okay. Now tell me which of the following is a valid CDF. You notice one thing here. Do you notice one thing about the solid dot? The solid dot at the start of this line or the end of the line? For every line, this is a start, right? This is the start of the line. So which means the solid dot cannot be end. It cannot be at end. At end, it will be actually, if there is a jump, then it will be the shallow. It will be a circle, right? Circle means there is no value here. So tell me which is the valid CDF? First one or the second one? Yes, the first one, right? Because at the start there is a solid dot. Okay, the first one. Great. So the second one is not valid. So this is the valid CDF. Okay, this is correct. This is wrong. Why that is the case? It is actually called with respect to this particular number. Let's suppose this is 1. At left, it is not continuous. At right, so what is the continuous? These things you will get to understand. Actually, the value of f of 1 and the value of f of 1 plus, capital F of 1 plus is same, right? This is same. So that's called right continuous. Okay, which means the value of 1 and 1 plus just immediately after 1, extremely near to 1, the values are actually same. But this is not equal to f of 1 minus, which means if we just go little, very very little left to f, left to 1, then it is not same f, not same as f of 1. So this is called as right continuous because 1 and 1 plus is equal. So you can say that solid dot is on the start. Okay, the solid dot is on the start. Another way of saying is it is another way of saying it is right continuous. Okay. So let's see more example. Probably you will understand more. So they are saying find this if the CDF is given. Yeah, they have done the different thing. They are saying the CDF is given. Now you find out the PMF. Okay. If CDF is given, then how to find out the PMF? In case of continuous, if we need to find out the PDF, then we could have differentiated this. But here what we will do, we don't need to differentiate on anything. See, this f of 1 is, for example, it is just probability of 1, right? F of 2 here is nothing but probability of 1 and probability of 2. So if f of 2 and f of 1 is given, then can't you just subtract both of them and find out the probability of 2? Actually, these things we have already done here. Okay. Okay, not I think in this lecture, but yeah, in the module 1 we have done. So what is f of 3? You can just revise the module 1. We have already done this. It is f of 1, p of 1 plus p of 2 plus p of 3, right? Or maybe in other words, f of 2 plus p of 3. So if these f's are given, then can you find out this p? So I think yes. How? This p will be f3 minus f2. You can just subtract the previous one. So it is f4. It is just a jump, basically. It is just a jump. Jump will be jump will be this f value at 4 and f value at 3. So this is f value at 4. This is f value, capital F value at 3. So this is just a jump that we are interested in, which is a probability, right? These are the jumps. Okay. Every probability just a jump here. Are you getting? Okay. So let's see more example. See here, every probability is just a jump. So it is just a jump. So this is the probability. This is also the jump. Okay, in case of discrete. Okay. Now see which of the following is your valid CDF. Okay, let's just see. Is A valid? I think it seems like a valid CDF. Is B valid? Uh, B is not valid because this is at the start, right? I mean, at the start it should be solid. So that's why it is not valid. What about C? I think at the start it is solid. I think this is valid, right? What about D? At the start it should be solid. I think E is valid, right? No, E is always increasing. So that's the reason it is not valid. Always increasing. D is not valid. The reason is that the CDF, initially the CDF, let's suppose it is starting from 0. So initially the CDF must be 0. So that's why it is not valid. Okay, A and C. Let's see the answer. So A is valid. This is true. C is valid. And these are invalid. Can you write the reason? This is okay. Why this is invalid? Because solid dot must be at the start. Why this is invalid? Because because minimum value of CDF must be 0. Why this is invalid? Because the maximum value of CDF must be 1. Okay. Okay. These are the reasons which are written. It's not valid because it is not right continuous. Right continuous means solid dot. Okay, solid dot should be at the start. It is the minimum value. Minimum value. It is not valid because it is not non-decreasing. Is this? Oh, sorry. It is also decreasing also. Okay, and decreasing also. Basically, it is not increasing actually. It is decreasing also. Right? It is decreasing, which is not possible. Understood the CDF, right? So this is easy question which you can try as an homework. Answer is there on the next page. Or if you want, we can also try quickly. Let's just try this quickly. So what they're saying, which of the following is not a property of the CDF? Okay, not a property. CDF must be from 0 to 1. Yes, this is a property, right? This is, I mean, minimum and maximum value should be like this. If you go, if you reach to infinity, then this must be 1. It is okay. If you reach to minus infinity, it is 0. It is continuous at every place. What do you think? Do you think the CDF must be continuous? No, right? No. This is false. For discrete random variable. Okay. Okay. And now what about this? Isn't this x greater than or equal to x? Yeah, this is true, I think, right? Okay, this is okay. Fx is an increasing function of x. Is this increasing? What do you think? Does this always have to increase? This is false, right? Need not always increasing. After some point, it will be constant, which is 1, right? After some point, it doesn't increase. And takes 1. Okay. So I think these two are false. So F and D are false, right? Yes. So it must be non-decreasing, may not be increasing. Okay. Now let's see the expected values. So which means how to find out the expectation. I mean, you already know this, but in case of continuous, let's just again do some little more practice. So how to find the expectation in case of continuous also? From minus infinity to infinity, we want to find out the expectation. Earlier, we used to sum over all the values of x. Now we will be integrating over all the values of x, right? X into f of x dx. Okay, cool. So if you want to find out the expectation of any function of random variable, then this is called lotus rule, right? Which means you can put this gx here and you can do the similar calculation. Okay. For example, you want to find out the expectation of this x. Then how to do it? You will be integrating x into fx. So which is 2x square. Integrating 2x square from minus infinity to infinity, which is from 0 to 1. So you can integrate from 0 to 1, 2x square, which is 2 by 3. Okay. For example, if you want to find out the expectation of any function of random variable also, then also you can do it. How? You will be integrating e power x fx, which is integrating e power x 1 by 2, right? From 0 to 2. So if you integrate from 0 to 2 e power x 1 by 2, you will be getting this, which is the expectation of e power x. Suppose they have given something like this. Now they are saying that this a and b are unknown. Okay. This PDF is defined like this. Now they're further saying the expectation of x square is known to you, which is 1 by 6. Then can you find out the value of a and b? Let me know. Is it possible to find out the value of a and b? See, one equation that you can make is something like this. You can say, here that integration over minus infinity to infinity fx dx must be 1, isn't it? Which means integration over minus infinity to infinity ax plus b dx must be 1 because of valid PDF. So from here, you will be getting one equation from one equation in between a and b, right? You can write 0 to 1 because that's the only non-zero thing. So 0 to 1. Okay. So there, from here, you will be getting one equation. What is that equation? Maybe something like this: ax square plus bx, right? From 0 to 1, which is a plus b. A plus b is 1. Okay. This is the one equation that you have got. There will be another equation you will be getting using this. How? Integration of x square a plus b, ax plus b, which is from 0 to 1. It should be 1 by 6, right? Which is ax cube plus b, ax cube by 3 plus bx, sorry, this is x cube, right? So ax power 4 by 4 plus bx cube, right? So here, what is the integration of x? This is x square. What is the integration of x square? Tell me. Yeah, x power n plus 1 by n plus 1, x cube by 3. So here, what is the integration of x square? It will be bx cube by 3, right? Just like this. So I think it will be 1 by 6. So there will be from 0 to 1. So I think it will be a by 4 plus b by 3, something like this, right? I'm not doing the calculation. It is there on the next page. So something like this. Okay, sorry. It is a by 2. Yeah, it is a by 2. So minus 2 and 2. These are the two values. Okay, these are the two values that we are getting. Okay, it was easy question only. Now let's see more questions. For example, this is given. They're asking you to find out the expectation of x square. Can you do this? as an homework. This will be integration from, 0 to 1, there will be some different quantity. 1 to 2, there will be different quantity. Okay. 0 to 1, you can do x into 2x by 3 plus 1 to 2, 2 by 3 x, 2 by 3 dx. Okay. Similarly, you need to do for expectation of x square. So the answer is on the next page. I'm just writing it. Okay. Cool. Similarly, this is also the easy question. I think you can find out the answers, which is on the next page. You can try this as an homework. So now you know how to find out the expectation in case of continuous also, right? That's also easy. For example, this, you can try this as an homework. Expectation of this function of random variable, you can put directly. So it will be basically 3x square into cx by 5 dx. C value you can find out, right? By the integration. Okay. Which is 0 to 10. So these are the easy questions only. So I'm writing this as an homework because answer is also there on the next page. Now let's just see what is the joint PDF. Okay. Which means joint PMF we have seen. Now let's just see how to deal with the joint PDF. So which means that you have a PDF, but in this case, the PDF will be the joint. It is also easy. For example, the joint PDF, maybe let me just show you the example. Just a second. Yeah. So the joint PDFs will look something like this, right? I mean, it will be the function of x and y basically. Okay. For example, it will look something like this. Okay. The function of x and y. Instead of just x or just y, it will be the function of x and y. So notice here, there will be the relationship between x and y. Okay. There might be, there might not be. I'm not saying there will always be, which means here they are saying that y is from 0 to x and x is from 0 to infinity. Okay. X can take the value from y to infinity or 0 to infinity, whatever you like to say. Okay. So there's a relationship between x and y in this joint PDF, right? So till now we have seen how to find out the expectation and these things. Now we will be moving towards the joint PDF, and in case of joint PDF, let's suppose they ask you to find out the expectation, okay, in these complex cases. So let's just see that how to do it. Okay, just a second. So should we resume this discussion tomorrow morning? Let me know. Okay. So this joint PDF and these things that we need to understand. And then we will see the expectation in case of joint PDF and other examples also. Okay. So let's just do one thing. Let's just, have this discussion till this point only. And tomorrow we will be seeing more things about this joint PDF and these things, right? These are the easy things. Don't worry. Don't worry. Like, don't think that these are the tough things. These are the easy things only. For example, this joint PDF is given. Then they may ask you to find out the expectation. They may even ask you to find out the conditional expectations. For example, they may ask you to find out the conditional, PDF. And then later on, we will be having the examples where they may ask you to find out given this joint PDF, they may ask you to find out the conditional expectations also. Okay. In case of discrete, we have done it, but in case of continuous, we need to do it. Okay. So that you get more confidence. Will you be wondering that in this year, GATE DA has had this question? I mean, they have given the joint PDF and they have asked the conditional expectation. Okay. I think I might be having the question. Not sure. Let me just see quickly. Yeah, right. So you see here this question. They have given the joint PDF and then they're asking you to find out the conditional PDF. This was the question number 59 in this gate, which means gate 2024. Okay. In gate DA 2024, they've asked you regarding the joint PDF and the conditional expectation. So once we cover this joint PDF and the questions related to that, for example, conditional expectation, these things, then this question will be very much straightforward. Okay. This is very easy question once you understand the basics, right? So let's just continue this discussion and let's just understand the basic behind these things. And then you will get to solve these questions very easily. Okay. So maybe you might be thinking that we are going on the slow pace, but this way you will be learning. I mean, this probability is little tricky than than linear algebra. So you will be learning it. I mean, your mind also needs some time to consume these things. So that's why we are running it little slow. Okay. So don't worry. Like, we will be completing each and every topic in very much detail, but I'm just going little slow. Okay. Cool. So let's just continue this joint PDF and these things tomorrow. Okay. Thank you so much. Thank you, everyone. So we will be continuing from here.